In this problem, it says that there's a cat that's walking in a straight line um, along the x-axis with positive direction to the right. And you take measurements of the cat's motion, make a graph of the cat's velocity here on the y-axis as a function of time. So you can see that the graph here, it looks like this green line. And in part A, we're supposed to figure out the cat's velocity at 4 seconds and at 7 seconds. Well, that one's not too bad. See, at 4 seconds, that would be here on the x-axis. And it looks to me like the cat's velocity is 3. So I'm going to write that down. In part A, at 4 seconds, the cat had a velocity of 3 centimeters per second. And it also asks at 7 seconds. So let's take a moment to think about that. Like, you have a negative velocity. So I'm going to estimate that at -1 or -2, something like that. Let's just call it -1. So -1 centimeters per second, approximately. And what else? Actually, wait, let me just think about something about that estimate. It goes from 8 to 0 in 6 seconds. So if I take the 8 and that it dropped and divide it by 6, I'll get 1 and 1/3. So that means that every time you move 1 second, you drop 1 1/3. So technically, when we went from 6 to 7, you went from 0 here to -1 and 1/3 here. So instead of calling it -1 centimeters per second, I really should say -1 1/3 centimeters per second, or -4/3 centimeters per second, otherwise known as, if I did that math, -1.33 repeating centimeters per second. Okay, so that's part A. Part B says, what is the acceleration of the cat at 3 seconds? All right, so let's take a look at where that is. 3 seconds is here, and we're looking for the cat's acceleration at that point. Technically, the acceleration at that point should be the slope of the line in that region. And to get to the slope of the line of that region, because it's a straight line, we could just use the slope function, the delta y over the delta x. We technically have kind of figured it out by doing part A. We knew that it drops 1 1/3 centimeters per second every time you move to the right 1 second. So that means that, and that slope is pretty constant because it's a straight line. That means that the slope at this point is going to be -1 1/3 or -4/3 or -1.33 repeating. So I'm going to say it's -1.33 centimeters per second squared is the acceleration at 3 seconds. And it also asks at 6 seconds, what's the acceleration? And at 7 seconds, what's the acceleration? And, at 6 seconds here, the slope is actually going to be the same slope here. So if the slope here was -1.33, it's still going to be the same slope here, -1.33. So the acceleration is the same. Also at 7, assuming that this still is a line that continues, the slope is still -1.33. So our answer is it's the same acceleration at t equals 3 seconds, at t equals 6 seconds, and at t equals 7 seconds. In part C, it says, what distance does the cat move during the first 4.5 seconds? Let me erase this for a second here. There's two ways to think about the distance move that the cat moves during the first 4.5 seconds. One way to think about it is to look at the shape of this area that's generated by the velocity function. And if we could find the area of this quadrilateral, then we would be able to um, calculate the distance that the cat moves, because the area under the velocity curve is going to be the distance that it moves. This graph here, this area here, could be split into two parts. A triangle up here, whose area is 1/2 base times height, and a rectangle here whose area is length times width. Calculate those two areas and then add them together, and that'll give you the distance traveled during that time. Another way of doing it is to use a formula, which actually kind of does a similar thing. The formula is that delta x, as in the distance traveled during an acceleration, is equal to the initial velocity times the time that we're thinking about, plus 1/2 times the acceleration during that time period times the time squared. If we use that formula, we should be able to get to the same answer. So let's plug in some numbers in here. Delta x is going to be equal to the initial velocity. Notice that the initial velocity here at time 0 was at 8 centimeters per second. So I'll put 8. And the time period that we're thinking about is during the first 4.5 seconds. So it's 8 times the t value of 4.5 plus 1/2. And we now know what our acceleration is. It was that negative 4/3 there. So I'll just write negative 4/3 there, so I don't have to round anything. And then the t is going to be 4.5, but you square it. Okay, so now we're going to toss this in our calculator. You'll have 8 times 4.5 plus 1/2 times negative 4/3, then times 4.5 squared. That gives me a delta x of 22.5, and that should be in centimeters. And if you were curious about whether or not we could do the same thing here, let's see. So I'll do this calculation using red color. If I'm focused on the rectangle first, the distance from here to here is 4.5. Its height looks to be about 2 from, like, say, here to here. So the area of that rectangle itself would be 4.5 times 2. So that'll be 9. That's the rectangle itself. For the triangle, the base of the triangle is 4.5 still. The height looks like it's from 2 to 8, which would be 6. And a triangle's area, as we said, is half base times height. So it's 1/2 times 6 times 4.5. Half of 6 is 3. And so now we have to do 3 times 4.5. That'll give us 13.5. That's the area of the triangle. And now we take the area of the triangle and add it to the area of the rectangle. So we'll just add 9. We get 22.5 as the combined area using the triangle and rectangle visualization. But of course, you could get the same answer using this formula here. In the next part of part C, it asks for the distance during the time frame from 0 to 7.5. If we're doing that, basically the only thing that would change is that this 4.5 would be 7.5, and this 4.5 would be 7.5. The acceleration doesn't change. The initial velocity doesn't change. So those things are pretty constant. And then if I were to just amend my original calculations here, just change the 4.5s into 7.5s, I'll get, let's see, 22.5. And notice that's interesting because you should have traveled more, a longer distance between 0 and 7.5. So why are we still getting the same answer of 22.5? But also, like the explanation for why it happens that way is because the area here is actually canceled out by the negative area here. See, this is a negative area where the cat is technically got negative velocity. So it's traveling backwards and it's undoing its motion from the prior time frame from, let's say, 4.5 to 6 seconds. It's moving forward, but then from 6 seconds to 7.5 seconds, it's moving backwards. So it kind of undoes itself there, which means that if you run it to 7.5 seconds, it's still going to have a total displacement of 22.5 because the last 3 seconds of travel have canceled itself out. Okay, so hopefully that makes sense. And in part D, we're supposed to sketch clear graphs of the cat's acceleration and position functions, assuming that the cat started at origin. Well, the what we have right now is a velocity function. So the graph represents a velocity function. And if we take the integral of the velocity function, we could get to a position function. So to go from here to here, we would take the integral. And then to go from a velocity function to an acceleration function, you could take the derivative. So we could do that. First, we need to think about what the velocity function is. If you look at the velocity function, it's basically one big old line that's got a y-intercept at 8 and has a slope of -4/3. So if we were going to write that in y equals mx plus v form, that would be y is equal to -4/3 x plus 8. Put into the kind of symbolism of physics, the y here is actually our v of x, and the -4/3 is the slope of that function. X in here is actually time, and 8 is just the y-intercept there. And if I were to put that into function format, it would be v of t is equal to -4/3 t plus 8. So that's what we have here. It's easy for us to take the first derivative of that to get to our acceleration function. The first derivative would just be -4/3, and the 8 would go away because it's a constant term. For us to integrate this, I'm just going to take that velocity function, integrate it. I'll get using the kind of the reverse power rule. I'll get -4/6 t squared plus 8t, and then technically there's a plus c there. And I know that at 0, this should be 0. So, doing that back work, we kind of can conclude that the c constant of integration is also 0, because at time 0, our position should be 0. And so that c kind of cancels out. And so now we have these three functions here, which are our position function, our velocity function, and our acceleration function. And we can now sketch clear graphs of them. So let's try to do that now. You've got -4/6. I'll write that as x squared plus 8x here. Let's see, zoom in. So our position function looks like this parabola here. And our velocity function is that line there. And our acceleration function is just -4/3, which is a line. I have to type it in as y equals, so I can get that line. All right, those are the three graphs that we have.